Hi all, welcome to this, the first video in our series looking at hydrosphere. Now this is going to be the obviously next topic as part of Unit 1 in physical geography that we're going to be looking at, and we're looking at this now so that we can link it in with the assignment that we're going to be doing shortly. Now to get started, a very quick look at the general topic outline for hydrosphere. Now there looks like there's a kind of fair amount of points here, but we do tend to meet quite a lot of them in a fairly short space of time. So the first things we'll be looking at is the global hydrological cycle. We'll also be looking at drainage basins and the water balance as a part of this opening topic, and we're going to look at these areas in today's video. Once we've done that, we'll start to look at some river features. We'll be looking at the formation of V-shaped valleys, waterfalls, meanders and oxbow lakes, and we'll also then look at hydrographs and their interpretation. Now, let's just get started today, and let's start by looking at the global hydrological cycle. Now, the global hydrological cycle, or as some of you might have heard it known, the water cycle, in the basic sense, is understood quite well. But what we start to do when we look at it in geography is we go into a little bit more depth about what all of these different parts of the cycle are. Now, some of them you'll be familiar with, some of them you won't be, so we're going to go through all of them today. Now, we start over here with evaporation. This is always treated as the start of the cycle. The sun heats up, some of the large bodies of water in the earth, be they oceans, be they lakes, etc., and it causes evaporation. This moisture rises in the air. As it rises, it cools and it condenses, and it moves, and you have a process of advection, where it is blown over land, and eventually you're going to get precipitation forming. Is this rainfall? Well, it could be rain, snow, sleet, what have you, but as this precipitation falls, some of it is going to make its way straight onto the Earth's surface, and that's going to be known as throughfall, and other bits of it are going to get caught up by different things, and this is where interception comes in. Now, interception happens largely by plants, trees, etc. Now, for the rainfall that does get intercepted, we are going to either see some of it stored in the vegetation, some of it taken in by the plants themselves, and we're going to see the rest actually make its way to the Earth's surface by a process known as stem flow. And that's literally where we've got droplets of water trailing their way down leaves, tree trunks, etc., making their way to the Earth's surface. Now, let's say you'll have some rain that just goes straight through, and that's known as throughfall. And some of that, again, will land straight on rivers. And that then will be known straight as surface runoff. And that's water that is in watercourses, rivers, streams, etc. that is travelling somewhere. Of some of that water and the rest of the water that falls on the land will go into the ground itself. Now, the first biggest process we have here is infiltration. And that's where the ground acts like a sponge and it's soaking up some of that water straight away. Now, some of that water is basically going to flow through the land very, very quickly, and we know that is through flow. Some of it is going to then drop a little bit deeper, and we then start to see another process happen called percolation. Now, percolation is a very slow process, and it's water droplets making their way through, individual soil particles or around individual soil particles to get deeper into the ground. Now, some of that water is going to continue to flow, and we know that is interflow, and it's a reasonable pace, and it flows through the ground, and it will, dependent on the geology, eventually meet up with streams or other large water bodies, and the rest of it will make its way either into groundwater storage, where it can remain for a long time. We could be talking the order of tens of thousands of years plus. For this, the length of time we can be looking at groundwater storage happening for. And some of it we're going to see operating as groundwater flow and base flow as well. And these are both just flows of water that we have travelling through deeper areas in the Earth's crust. Now, we've got a couple other bits on here that I've not made reference to yet. We've got channel storage, so this is fairly straightforward. This is the volume of water that we have that are actually inside a river at any given point in time. Now, this is a transfer. This is water being moved from one place to another. And the water that is moving we know is channel flow. Now that water will eventually be discharged into a larger body of water, be that a lake, the sea, etc. And that forms our river discharge. Now, last bits that we've not mentioned, over here you see we've got transpiration. Now, transpiration is the process of evaporation happening directly from plants. So it is where we have got moisture that is being released by plants into the atmosphere. A term you'll also see quite a lot is we tend to bracket transpiration and evaporation together, and we would term that as evapotranspiration. And all it is a catch-all term for both total amount of evaporation and total amount of transpiration. Now, what we've got here is a different way of representing that information that I was just talking about. Now, this is where we're looking at it more on the scale of one drainage basin, so one river system, as opposed to the previous diagram that's more looking at a global system. But if we think about it in the scale of one river, we've got inputs, outputs, transfers, and stores of water. So water or moisture is input into the system by precipitation, and we focus that as our sole input. We've then got three outputs that we think about straight away. We've got evapotranspiration, or transpiration and evaporation, which are both leaving the system, and we've got river discharge. However, how we get to these is, can be variable. So we've got precipitation and we've got storage and interception. We've got some of that rainfall is caught by trees and it stays there for normally a short period of time. By stem flow, or leaf drip is another phrase for this, we see a transfer of the moisture that's been intercepted, and it then goes to the ground, to the earth's surface. It then gets kept as surface storage. That can then either go as surface runoff, and it then goes into channel storage, which then again goes into channel flow, which comes out as river discharge, or it can go into infiltration. Now, so that's where we've got the moisture on the surface of the earth that's actually going into the earth's surface, and it then gets stored in the soil. Now again, there's a couple of options for what can happen here. Some of that then gets stored in vegetation, it gets drawn up into plants, where it will eventually be transpired out into the atmosphere. Some of it will then travel through the earth's surface straight into a river, where it then gets put into channel storage, then into channel flow, and into river discharge. And the last of this will then travel deeper into the earth, and it will percolate through soil, through rock, into groundwater storage. Again, some of that will then move as groundwater flow or base flow into a river system, which will then move through that river system and be given out as river discharge. Now, there's a lot of information here, but the key point is that it is a system that can operate in a very straightforward fashion. A point, that I should have mentioned earlier, any of the water that's been intercepted or is being stored in the surface, and to a point the stuff being stored in the soil, can be evaporated out. If there's enough heat on that from the sun, it will evaporate away. Now, when we talk about drainage basins, which is what we've just been referring to now, a drainage basin, simply put, is one river system. We look at two major measurements that we use to discuss drainage basins. We look at drainage density and we look at stream order. Now, drainage density is when we're looking at the total length of rivers in that system divided by the total area of the basin itself. And that can vary with a couple of different factors. So, land use. When we look at land use, if we've got very, very little vegetation in an area, drainage density will be higher. Because if we've got very little vegetation, there's less opportunity for moisture to be hidden away, basically, by plants and other things like that. So we'll have more small streams and rivers, which increases the overall drainage density. The older a system is, the older a river system is, the lower its drainage density is. Conversely, with relief, the more uneven relief is in an area, the more or the higher the drainage density is. And finally, precipitation. The more precipitation and the more intense precipitation that an area gets, the higher the area's drainage density is. Now the last thing that we've got here is stream order. Now stream order is something, you look at this diagram, it looks a bit odd, but it's really, really straightforward. So first order streams are streams that have got no tributaries, no other streams joining them. So these are the source of a river. A second order stream has two or more first order streams joining it. A third order stream has two or more second order streams joining it. A fourth order stream has two or more third order streams joining it, and so on. And this is something that we use to tell us how expansive a drainage basin is. You know, if you've got somewhere like the Mississippi is, you know, up at 10 plus orders of stream order, and it shows you how expansive that system is. Whereas if you go and look at a much smaller river system, you know, something like the Glen Rosa water is likely only to be second, if maybe third order. So it's a much smaller system. So we use that to tell us about the scale of the river system. Now the last thing that I want to look at in today's video is water balance. Now you look at this diagram and hopefully, if we take a wee moment to just interpret it a little bit, it's fairly straightforward. Water balance is just looking at, is a system going to be in a position of surplus or deficit with regards to groundwater? So we look at total level of precipitation, and now the actual numbers on this aren't terribly relevant for our purposes, but they do serve a nice purpose just in terms of setting the scene. So if we look at total amount of precipitation over the course of a year, and we look at the total amount of potential evapotranspiration, dependent on how those things are with reference to one another, can influence how much available groundwater there is in an area. So if precipitation is in excess of evapotranspiration, we are going to have a surplus, and we are going to see groundwater stores filled. As evapotranspiration rises, we are going to see the groundwater stores become depleted until we eventually hit a point where we are at a water deficit, where we are trying to take more water from a groundwater store than we are replacing it with. If we then move on through the year, and as happens, evapotranspiration decreases. And again, thinking about the reasons for this, we're basically talking about seasonality here. So we're looking at this from a northern hemisphere point of view. You know, warmer in our summer, colder in our winter. Colder it is, the less evaporation you've got, the less transpiration you'll have. So as this drops off, and we start to see precipitation increase, we've got a period of recharge where we are rebuilding that groundwater store from the depletion that it's went through over the summer. We then enter a surplus again, and the system repeats. Now this can become very, very important in areas that depend on groundwater for a large number of different things, primarily agriculture. If you know that you're having a very long, very hot, very dry summer, you know that this groundwater store is going to be depleted much quicker, and you then know that your period of recharge is going to be longer as well. So that can have an influence on how much groundwater you actually have to utilise. Now, I'm very aware there has been a lot of information in today's video, guys. I'm going to pull a stop to it here. We'll obviously discuss this stuff a wee bit more in class, and I will see you guys then.